This is a semi-transparent mirror with a transmission of 50%. Half of the initial intensity goes through, and the other half gets reflected. So, how much goes through two mirrors? Well, it's a quarter of the initial intensity, plus a quarter of that, plus a quarter of that, and so on. So in the end, the transmission of two mirrors is somewhere between 25% and 50%, as you would expect. But what if I told you that the transmission of laser light can go all the way up to 100%? Well, that just sounds like complete nonsense. How can two semi-transparent mirrors be fully transparent? In general, oscillating electric fields are added, not their intensities. And the addition of fields which doesn't result in the addition of intensities is called interference. This magical trick is just a result of interference. At any point behind the second mirror, infinitely many scaled and delayed copies of the same field are added, where the delay between any two subsequent copies is equal to the time that light needs to make a round trip. Assuming that the field oscillates sinusoidally, if this round trip time is an integer multiple of the period, all fields are correlated and their amplitudes are added. Now the punchline is that intensity is proportional to the amplitude squared. So when a beam passes through a mirror and the intensity gets divided by a factor of 2, the amplitude only gets divided by the square root of 2. As a result, the amplitude behind the second mirror is half of the initial amplitude, plus half of that, plus half of that, and so on, which indeed adds up to the initial amplitude. But hang on, if all of the light goes through, then according to the conservation of energy, no light can be reflected. The reflected beams should cancel each other out completely, and they don't. When light goes from air to glass, some of it gets reflected. How much gets reflected can be calculated from the two refractive indices. In this case, it's around 4%. So we can model our mirror, which reflects 50%, as an interface between air and some material with a refractive index of around 6. I'm gonna call it metaglass. Now, although the reflected and transmitted intensities are equal, the fields are not. If light goes from air to metaglass, they are equal and opposite. Whereas, if it goes from metaglass to air, they are equal. Thanks to this flip in the sign, the reflected beams cancel each other out and energy is conserved. Now, the truth is that metaglass doesn't actually exist. Most materials have a refractive index between 1 and 2. Every mirror is a piece of normal glass, where one interface is coated with a thin layer of silver or stacked dielectric layers. But wait, what about the other interface? Well, in that case, we need to apply an anti-reflection coating. Again, the idea is that the reflected beams cancel each other out. But there is a twist. This can only happen for a certain refractive index. Okay, now let's see if this really works. I glued the mirrors onto kinematic mounts so that they can be tilted, and then I added a pinhole and a laser. Next, I turned on the laser and tilted the mirrors until all reflected beams went through the pinhole. Whenever I pressed on the table, the transmission changed. According to our model, the peak transmission should be 100%, in which case the reflected beam has to disappear. But what I saw was that the reflected beam was always brighter than the transmitted beam. To understand what's going on, we need to understand what the word coherence means. Let's say that you have an ideal laser and you keep it on for just 1 second. The result is a pulse with a length of 1 light second, or 300,000 kilometers. Now imagine a cavity which is twice as long. The transmitted pulses don't interfere because they don't overlap. So let's see what happens when we put the mirrors really close to each other. Voila! The transmission is close to 100%. Now, a laser beam is obviously not a pulse. It's continuous. But we can pretend that it's a series of pulses which are mutually uncorrelated. In general, when two delayed fields are added, the total intensity is the sum of the two intensities plus an autocorrelation term. Now, if the time delay exceeds a certain coherence time, this autocorrelation term disappears, and with it, interference disappears. What makes laser light special is that this coherence time is very high. Now, at the beginning, I mentioned that the round-trip time needs to be an integer multiple of the period. This is known as the resonance condition. An equivalent condition is that the round-trip length needs to be an integer multiple of the spatial period, or wavelength. Or that the frequency needs to be an integer multiple of the fundamental frequency. Decreasing the cavity length increases the fundamental frequency, and at the same time, it makes the transmission peaks broader. Decreasing the reflectivity of the mirrors makes the transmission spikes not only broad, but also shallow. At extremely low reflectivities, the transmission of non-resonant frequencies is still close to 100%, simply because the first transmitted field is way more powerful than all the other transmitted fields combined. On the other hand, at extremely high reflectivities, it goes to almost 0%, because all transmitted fields are approximately equally powerful. The transmission spikes are deep and narrow. By shifting the spikes, we can record any spectrum that can fit between two spikes. For instance, the spectrum of our laser. Okay, that's not very interesting. But look what happens when I increase the current. The cavity spectrometer was invented by the French physicists Fabry and Perot at the end of the 19th century, and it revolutionized spectroscopy. Its resolution was unmatched, because in contrast to all the other spectrometers which existed at the time, the resolution of the cavity wasn't limited by its size. It could be enhanced by a factor related to reflectivity called finesse. Fabry later recorded a high-resolution absorption spectrum of the atmosphere, and he discovered the ozone layer. By the way, spectroscopy wasn't the first application of the cavity. Before that, Fabry and Perot used it to measure the distance between two electrodes. And believe it or not, this forms the basis for measuring gravitational waves. Now, notice that there is one more quantity that we can measure. It's the speed of light, which happens to be proportional to the medium's density. So we can also measure sound. Okay, I think it's time to end this video, and I'm gonna end it with a cliffhanger. As you know, in reality, the laser beam is made of discrete energy quanta called photons. Though, to measure them individually, we first have to decrease the photon rate from trillions of photons per second to, let's say, 10 photons per second, using a series of neutral density filters. The funny thing is that even when we place the filters in front of the cavity, we still receive 10 photons per second. This doesn't make any sense if you imagine the photon as a little flying ball. Because I mean, how does the ball know that there is a second mirror?